what did we call this circuit?
Counter.
Yeah, this is a counter because we have a flip-flop and we have this like counter or this adder right here. All it does is just adds 1 every time. And if we wanted, actually, maybe instead of just a counter, maybe instead we could have like an accumulator sort of thing where maybe we have like an input logic and maybe we have like an A input.
Can you build the lines?
I don't know which.
That's good.
Yeah.
That's good.
All right, I'm gonna fall asleep. Okay. So as you can see, so we could have an A of I input, and maybe instead of adding 1 every time, maybe we go and add A of I. Sure, makes sense. We go and synthesize this, and you'll see the circuit hasn't changed that much. Now we just have this kind of generic adder cell. Now it's taking in both the flip-flop output and also the input. This input, right, this is probably going to be like going to be driven by some other like top-level module. But I guess like kind of absorb this for a second. So which part of this circuit is the combinational logic?
The add.
Yeah, it's going to be like this cell right here, the adder cell. It's combinational because it will take in the like inputs to the module. It will take in like the ports, and it will take in the current state, and it will turn that into whatever the value of like the next state should be, and it will probably turn it into, I guess, whatever like the output should be. So that is combinational logic. It uses like the current state and then turns it into like the next state. Okay, so then question for you. If the flip-flop, we say maybe is in the state of storing the value 5, then what would like the next state on the next cycle be? Assuming maybe this A of I was like 1. So assuming that the state was 5 and the input was 1, then what would the next state be?
6.
It would be 6, right? And that's kind of the whole idea with like actually like thinking about combinational logic. It's like that you want to go from whatever your current state is into whatever you want your next state to be. So if you want like a counter like this, it's really easy. You just add 1 to your state every time. If you maybe had something maybe more complicated, maybe you are building some sort of serial communication like receiver, then maybe you instead would want to, instead of just having like a simple kind of flip-flop that keeps track of like the count, maybe now you actually have your flip-flop encode some certain state that you want to, like that you want to be in. Like if you are receiving the start bit of some UART signal, and then on the next cycle, now you want to say that you're receiving the first bit of your data signal. So the idea with flip-flops is, it stores your current state. And this goes into the next idea, which is state machines. State machines, this is the concept that you can build a circuit that will change from state to state in order to implement some sort of functionality that takes place over multiple clock cycles. So that is a state machine. A state machine will produce some sort of functionality over a set of multiple cycles. And in this lecture, I wanted to give some examples of state machines, and while also like synthesizing them and showing them on digital.js online. Yeah, Mark.
So the counter file.
I can, absolutely. This is the counter file. Yeah, and so here is the flip-flop logic right here. Good. Okay. So the first state machine that I would like to go over, this is an example that I've gone over in CSE100, but I just really like this example. The example is, assume that we are receiving in a number, and maybe we're receiving in the number serially, like 1 bit after another. We're receiving maybe like we receive a 0, we receive a 1, we receive a 0. And then at the very end, once we have received like all the bits in a line, imagine that we've concatenated them all together, and we want to determine whether that number is divisible by 3. Okay, so if we start out, let's say our number that we are receiving is the number 0. So we've just received our first 0. Question, is this 0 divisible by 3?
Yes.
We would say, actually, yeah, we would say 0 is divisible by 3. So we would say, maybe this has a remainder of 0. Okay, let's say we received a 1. Then what would this remainder be?
1.
This would be remainder 1, so this is not divisible by 0. Okay, let's say now we receive a 1, and then we receive a 0. So we receive a 1 first, then we receive a 0 after that. Then what is this remainder?
2.
This would be remainder 2. Okay, imagine now maybe instead we received a 0, then we received a 1. What is this?
1.
Yeah, this is remainder 1, right? And what if we received 1 and then we received 1 again?
That's
Remainder 0.
This would be remainder 0. Okay? Well, notice that if we have maybe something that is like remainder 0, then we can effectively just realize that, well, any time that we receive like another 0 on that, like let's say we have something that is remainder 0, so I'll put in like the number 3 here to denote that. So let's say we just received something that is remainder 0, and we just receive another 0. Okay, what will the remainder of this be? So
Zero.
yeah, I think it would be 0. So for example, if we have maybe the number what is this number right here in binary?
6.
Yeah, so this is 6 in binary. So let's just say we received 6, and now we go and receive a 0. What is this new number?
12.
This is 12, yeah. So actually, anytime we receive a 0, this is the same thing as multiplying by 2. So if we receive a 0, same as 2x. Okay, let's say we receive a 1. If we receive a 1, then it's the same as 2x, but plus So let's say we receive the number 6. So whatever, 110. So if we receive the number 6, and then we receive another 1 after that, then what is this new number? This would be 13. Yeah, so this is the same as multiplying by 2 and then adding 1, because now we've shifted in this extra 1. Okay, it makes sense. So this would be like if we receive, here I'll do that. If we receive a 1, it's the same as 2x plus 1. Okay, and note, right? So if we're checking if a number is divisible by 3, that means that there are only 3 possibilities. We either have a number that is remainder 0, remainder 1, or remainder 2. We can't have something remainder 3, because that's the same as remainder 0. So cool. So now we could potentially make like a state machine. We could just check like, okay, well, what is the state that I'm currently in? Like if I'm currently in the state where I've received a number that has a remainder of 0. So if I've currently received a number that's remainder 0, then the question is, if I receive a 0, then I can know what my next state is. And if the next number is 1, then I also know what my next state is. So cool. Okay, let's go and kind of draw this out on the iPad. Okay, so let's make our states be 0, 1, and 2. Cool. Okay, let's say we are in a number that is remainder 0, and we receive a 0. What is our new state going to be?
0.
Yeah, if we receive a 0, it's the same as multiplying by 2. So let me write that at the top too. So if we receive a 0, so 0 is multiplied by 2. A1 is 2x plus 1. Okay, yeah, so if we are in a number like remainder 0, so if it's 3 or 6 or 9, and we receive another 0, then this will just loop back to itself. Now we are once again a number that is divisible by 0. If we receive a 1, then what is the new state? So if, let's say we have received the number 3, and we receive a 1, then this would be now, wait, sorry, 7, right? And 7 mod 3 is 1, right? So if we receive a 1, then this would now transition to state 1. Feel free to stop me if I make a mistake. I might intentionally make a mistake. Who knows? Okay, cool. Maybe state 1 now. So if we are in, maybe if we're currently number, give me a number that's one more than a number divisible by 3. What's the potential number here? What was that?
7.
I like 4. Okay, so let's do 4. So let's say we have 4 and we multiply that by 2. What is that remainder?
2.
Yeah, so if we have 4 and double it, that becomes 8. 8 would be a remainder of 2, I think.
The remainder doubles, but it remains mod 3.
Sure, right. Yeah. So
Which means that if your remainder is not 0, then then when it doubles, it will never return to 0 because.
Sure.
Yeah.
Right. Yeah. Okay. Now let's say it's 4, but now we shift on a 1, so this would be 9, right? And so what state is that? What state if we receive a 1 and we're in state 1? Okay, I will leave the rest of this for you to complete right now with the people around you.
Wait, so the input is 1, and then you receive another 1, and then was that?
The question is, okay, so the question is, I want to find every single possible arrow. So for every possible input and for every possible state, find where each transition is. So if we are in state 1, meaning if we've received maybe the value 1 or the value 4 or the value 7. So if we're in a number that is one more than the number divisible by 3, then the question is, where would we go next if we receive another 1? And it goes for this as well, go and complete this as well. Okay, take a minute. Feel free to discuss and kind of recoup. It's what the heck is Ethan talking about?
Wait, so I've got the stage 1 and then.
All right, I'll show you what I got. I may or may not have left an intentional mistake, so go and let me know what happened. Okay. This is what we got? Yeah, Albert.
From 2 plus 0, it shouldn't go back to 1.
2 plus 0. Wait, 2 plus 0. 2 plus 0?
Yeah.
Should not go back to 1.
And then 1.
Wait, hold on. So 2, so if we have the number 2, so 1, 0, and then if we receive another 0, that would be the number 4 now, right?
Oh, okay.
So I think that is correct. Makes sense? Okay. Leeway?
I think if you add a 1 to a number with the remainder of 2, it should just go back to 2.
Yeah.
Oh, okay. So if we have 2, so 1, 0, then receive another 1, that would be 5. And 5 is also a number divisible, or sorry, 2 more than the number divisible by 2. So yeah, so sure. So this would go to where?
It should just go back to 2.
Yeah, that's what I'm thinking too. Cool. Okay, is this what we got now?
This is a funny state machine.
Sure, yeah. Faster than a, I don't know, whole divider or something, or a remainder calculator.
I was thinking, yeah, of a linear shift register.
Sure.
Whatever the word for that is.
Yeah. Okay, cool. Now, let's kind of see what a circuit would look like for this. So let's go and implement this in Verilog. Maybe you could hopefully have this written down, or you can take a picture or something. I won't show it as I implement the Verilog. Okay, I'm going to pull it up in just 5 seconds.
These are classes that I should for CE you should take either.
The like side
Okay.
is more fun.
Yeah.
Well,
Okay, here is my remainder 3 units. So here I have input A of I. Notice it is just one single bit because we're receiving serially. And I will make this output, we'll call this like rem3, and we'll make it, I don't know. Well, actually, I guess, what should probably the size of this be?
2 bits.
Yeah, so this is probably 1 to 0. Yeah, cool. Now, what we should do is make probably our flip-flop. So our flip-flop, right, so there's 4 possibles, like, sorry, what am I saying? There are 3 possible options, right, 0, 1, or 2. So let's go and make a flip-flop that can store our current remainder value. So I will go and change all these to remainder 3. Good, that's good. I think that's fine. Okay. So we've now, so this code that I've started out with, right? I think we've finished all the flip-flop parts of this. But now the tricky part is figuring out how to build the combinational logic. Like this is the tricky part of making state machines. It's not the flip-flop. The flip-flop kind of just comes by default. The flip-flop means that you must have like a flip-flop that stores whatever state you want. But the combinational logic is actually the hard part. So let's go and make an always com block now. And the first thing by default, and I'll go and also drive this output right here really quick. Say sign 3 is equal to the flip-flop output. Okay. And then I will by default go and set the D input to Q. Now I'm going to use a case statement. And this is very similar to case statements or switch statements in C. This is how it works. So you will want to put in probably like the current state right here. And then you put in now, like for every possible value that this state could be, now you go and put that value. So here we're saying like if the state is 0, then I'm going to put begin and end. Actually, I guess I don't need that. That's fine. And then I can put if the state is 1, then I can put if the state is 2. Then it's always good to also just have this default case, just in case something weird happens. So maybe by default, we can just put this right here. So by default, actually this is probably not good. Let's do by default, it will reset to 0. Okay. So the question now is if we are currently in a remainder of 3, sorry, if our remainder 3 value is currently 0, so if we are currently divisible by 3, so if this is like number 3 or something, then the question is, what is the next state? In other words, what do we put here?
If AI is 1, then you want to set it to 1.
Okay, so if AI is set, then we can use this ternary operator, and we can say that now we want to go to state 1. Otherwise, we want to go to state 0. Does that make sense? Okay, and I think we can do something very similar for the other states. So for state 1, so maybe we currently have the number 1. Let's say we receive another 1. Then what is that next value going to be? If we've just received a second 1.
It goes to 2.
What was that?
It goes to 2.
I don't think it goes to 2.
It goes back to 0.
I think it goes, yeah, I think it goes back to 0. Because if we have the value 1 and receive another 1, that would now be 3 in binary. 1, 1 is 3 in binary. Yeah, so this would be 0. And then if we had received a 0, that would be the value 1, 0. So I think this would now be state 2. Then we can do this last one. So if we currently have the value 5 or something, and we receive a 1, then I guess it's 5 is kind of a tricky thing. 5, 11. So that would be 2 more, right? And the 0 case, I think, would be 1 more.
Why do you set
Things okay.
rem3d above the case block if it's going to be reassigned in every case?
Oh, good
Is that
question.
even necessary?
Yeah, why do you put this here? Actually, it's not necessary. I guess
You just anticipated potentially not assigning it in a case block?
that's exactly right. Yeah, so in the case where you
Didn't have default.
in the case where you don't have a default case, what will happen is Verilog will get upset at you, specifically system Verilog. Always com blocks expect that if you set a variable anywhere in your decision tree, like anywhere in your big mux tree, like in any one of your case statements or any one of your if statements, you must always be sure that there is a default value for it to fall back on. So just a good practice is anytime you ever modify a variable inside of an always com, just at the top, I just always go and put a default case just in case. And honestly, I could have done this as well. I could have just assigned it as an unknown value. And now in simulation, I would see a bunch of X's, and now I'd be like, oh, uh-oh, something bad happened. But it's much better to have an error, visible error that's a bunch of X's, as opposed to not receiving any error. You might, if maybe I was missing one of these cases, then the waveform would be very confusing. Yeah.
Also, why are rem3d and q 8-bit and not 3-bit? Or in fact 2-bit?
Is that what I did? Oh,
There is it?
No reason. Okay, cool. Let's go and test this out. Hopefully this works. And I will turn on optimizations to kind of simplify things down a little bit. I'm not actually sure if it will simplify things. I guess it does a little bit. Actually, this works. I take it back. Okay, that's fine. Synthesize. Okay, good stuff. So hopefully this kind of makes sense to you. Maybe I should have had you close your eyes for a second and imagine what the circuit would look like first before I ran synthesis on it. But hopefully this makes sense. So here we have this big case statement box. Notice, right, so with our case statement, we have 4 possible cases. We have 0, 1, 2, and then by default, 3. So in the 3 case, then now the input is set to 0. And then in all of these other cases, we see that they are connected to this other circuit element. And what are these circuit elements?
Muxes?
Yeah, so these are muxes, and each of these come from each of these little ternary statements right here. So what happens is now every single one of these inputs into this big case mux, into the wide mux, is now also being driven by a mux. Does this kind of circuit structure kind of make sense? It's kind of cool. Yeah, and note, right, that we are taking in this A input, this is the input to our what am I saying? This is the input to our system, but we also need to keep into account the flip-flop state, the state of our flip-flop. We need to keep both into account, and that is what then produces our input condition for our combinational logic, which then goes and propagates through until finally it arrives back at the flip-flop D input. Cool. Okay. Let's review. We're all oh yeah. Excellent. Okay. I'm going to show you something that you should probably always use anytime you use state machines. So I actually don't really like assigning numbered states like this. And the reason for that is because actually 0, 1, and 2 are not always the best state encodings for these. So that's kind of an interesting concept, maybe. But so for each one of these states, so we're saying like, oh, if it has a remainder of 0, then we are going to put into the flip-flop the value 0. And if it has a remainder of 1, we're going to put into the flip-flop the value of 1. But it's possible that maybe we run some sort of fancy analysis on it, and we find out that actually the circuit would run the fastest if, for some reason, the flip-flop, when it has a remainder of 0, maybe instead it actually runs faster if instead it stores like number 3. Like the flip-flop itself like actually stores number 3, even though that state corresponds to like remainder 0. And you can easily change these state encodings by using an enum. So enums come from C++ and C, I believe. Are enums in C?
Yes, there.
Thank you. Okay, enums come from C. And enums are only in system Verilog. So you may see a lot of like Verilog code, like online examples that don't use enums. And you should ignore them because enums are great and highly supported by just every single tool. But for some reason, a lot of like old textbooks are like full of old people that are scared of using like modern system Verilog features. Of all of the possible system Verilog features, I would say like enums are probably one of the like most safe features that you can use. And so, okay, let me go and show you the syntax for this. So here I'm doing typedef enum. Typedef meaning I can reuse this enum in other places. So by default, you just always want to call your state underscore t meaning like this is a type that we've just created. And now we can go and create all of our names for these variables, so our names for these enumerations. So we can say remainder 0. Maybe we can go and hard code this to a value of 0. And all this is we are just putting labels on numbers. So we're going to say like, oh, remainder 1 is actually just 1. So like anytime you see this like word right here, rem1, now just go and replace it with the number 1. And if I want to do rem2, on this I could actually say is equal to 3. And for data type, I'm going to change the data type to be 2 bits. So there we go. So now we can see that for some reason now we've made it so that rem2 is actually value 3. And then now we need to go and change our flip-flop to, instead of being logic 1 to 0, now we are going to make it state t. And now each one of these next state values we will need to grab from our enumeration names.
Do you have to use like the dot operator or something?
No.
Oh, very nice.
Yeah. Okay. Cool. So just by default, anytime you ever use state machines, just always use enums that are labeled state t. And note, so I explicitly said like 0, 1, and 3 here. If I wanted, I could actually just leave this off. And by default, enums will be defaulted to just assigning the numbers sequentially. So it'll be equal to like 0, then it'll be equal to 1, then it'll be equal to 2. So this is just the default behavior. So honestly, most of the time I just kind of leave this blank. And then if later on I decide I want to change it, then I go and change the encodings.
Can you specify like 1 and then they automatically go sequentially?
I think so, yeah. So I think if I said like equals 5, I think that would mean now this is 6 and 7.
Sweet.
Yeah. Cool. Also, yeah, you just want to be careful of your width here. Okay. Yeah.
So what's the advantage of having rem2 equal to 3 instead of 2?
Yeah. There's probably not in this example, but just as you change the variables that you are dealing with, I don't know if I can come up with an example on the top of my head, but I don't know. Sometimes it just helps to change the like your sum of products expression. Like maybe you imagine your sum of products expression, for some reason, will just get a little bit smaller if you just change rem2 to instead have an encoding of 3. You may notice, like, you can just try a bunch of values, and you notice for some reason when you change, one of these to a different encoding, for some reason it shrinks the amount of logic that you've used.
Is there a way to find out which number shrinks logic the most?
It would be something you would just have to do trial and error on.
Okay.
Yeah. Yeah.
Something like, for example, if it flips this from 0 to 1 to 1 bit flip, and from 1 to 3 to 1 bit flip analysis.
Exactly, yeah, right. So you actually, in a state machine, you want to minimize the number of bit flips generally. And yeah, that's for power reasons, and also that will shrink your logic that you use. Cool, okay, anyway.
I guess, did you try synthesizing this? Because I got like
Does it not work?
a error.
It should just work, but it's possible a small typo. No, yeah, it works.
Oh, wow, okay.
Yeah.
Yeah, I'm not really sure.
Sure, yeah. And yeah, so here I'll go and reset it really quick, and then if I want, we can look at rem3, it says 1, and then 0, I guess if I want to get to 2, there we go, 2. Yeah, and if I wanted, I could actually instead go and set like this to 1. Now I can go and synthesize it. Now we should see that
I think I got it.
looks differently. Oh, good. So now I can reset. Okay. And so if you watch this right here, so currently it's 0, then I can shift on 1. Is that, whoops, because I messed up right here. This should be, 0. And this, this is actually, okay, this is probably very important I should mention. Notice this didn't work because you should never assign like an actual constant value to a state t. I assigned it to 0, but what I did is I changed the 0 encoding. So actually what I wanted to do is just assign it to rem0. So that later on if I go and change what rem0 is encoded as, then I don't need to change like it anywhere else. I can just change it right here. Okay, hopefully this works. All right, actually, did that simplify things? Maybe it didn't. Okay, anyways, 0, 1. Oh yeah, there we go. So now you can see it says 1 up here, and then if I go and shift it in, now it says 2. Okay, any last questions as I move on to this example? Now, I want to talk about multiplication. So multiplication is a great application of sequential logic, like logic that takes place over multiple cycles where you need to keep track of your input and you also need to keep track of your current state. Okay, so imagine now we have a number, maybe it's a 4-bit number. So it's A0, actually, do it backwards. So A3, A2, A1, A0, and we want to multiply it by B3, B2, B1, B0. The common algorithm that we are used to, right, is we take this first number right here, and we multiply it by all of this number. And so maybe I can go and write that out really quick. Okay, and then what you do is you then take this number now, except now you concatenate this with like 0. Right? Because now you, instead of just multiplying by like whether this is a 1 or 0, now what you do is you multiply it by like whatever this is, 1 or 0, but then like shifted by 1. Good. I can go slower if that would be helpful. This should be a review from 100. Okay. Feel free to stop me at any point. Yeah. So then we can go and multiply this now by A. And so on. And now we can imagine that we do 2 and 3, and if we had larger widths, we could keep going. The first question now is, maybe we didn't want to do this over multiple cycles, maybe we just wanted to just, straight up just implement this. How could we maybe just do this combinationally, where we take in A and B? Think about that. So we could probably have maybe like a for loop, right? That iterates through. Maybe we grab like each one of these individual bits. Okay, let's go and see if we can implement just like a basic kind of combinational multiplier. Okay, here I have boilerplate, so we have A and B and Y. So if you were asked on a homework assignment, like for example, I think you're asked to make a multiplier in homework 2. If you were asked, it's like, okay, go and make a multiplier. Maybe your first thought would be like, oh, easy. Like, why is this assignment expecting me to take a long time with this? Like, I can easily just do a sign, y0 is equal to AI, and then just star BI. Good. Done. Let's synthesize this. It's still gone in the last one. Let's save. On. Okay. Do we think this is going to work?
Maybe.
You know, actually, I guess it kind of did. Okay, cool. The thing is multipliers are kind of a pain. Like, so adders, it doesn't really matter how fast they are because they're going to be like really, really fast in the grand scheme of things. Like your adder is probably not going to be the slowest thing in your design. It's possible, but probably not. The multiplier very reasonably could be the slowest possible thing in your design. And so if you go and just put a star here and abstract away the implementation, this is considered bad practice because there could be so much logic. Like this one like little X statement right here, this could be potentially like hundreds or maybe even thousands of lookup tables just to implement this very basic symbol right there. So therefore, it's good to actually implement any multipliers that you want to use. Or if you're not implementing it, at least grab it from like some sort of open source implementation. So okay, let's go and implement this as just a combinational multiplier, and then I imagine that should be a good enough place for you to start so that you can figure out how to turn that into a sequential multiplier. Okay, so we can probably do always com in. Like I said, we'll probably want to have a for loop. Maybe the first thing though is we can just put a default value for y of 0, just in case things get weird. So maybe by default we just set it equal to 0. Now we can have like for int I is equal to 0, I is less than, sure, let's do 8 for now, plus, again. Okay. Now, turn to the person next to you and see if you can work this out. See if you can figure out what to put inside of this for loop in order to properly produce a multiplication. I'll give you a hint, probably just do something like repeated addition along with shifting.
So basically do this
You can have a variable that has a running total.
But not in a combinatorial logic.
As long as it's localized within the always com.
Oh, what?
But because what will happen is it'll just sequentially keep adding like more, like it'll just increase the length of your like cascaded logic.
Okay.
If you remember, like we could have like an if, like in a for loop, we could just have a bunch of if statements that just now produces a bunch of muxes all in a line. The same way you could just keep adding like something over and over and over.
Okay.
Now I just have a bunch of adders in a row.
So having a bunch of adders is still better than doing like assign y0 equals AI.
Potentially, probably. Yeah. I would say it's something where you'd want to test it both ways. Doing any sort of multiplication is considered just very intrusive on your design. So if you ever want to use a combinational multiplier, like you're signing yourself up to like work with fire. So yeah, that's something where you definitely want to test both.
Oh.
Most likely, like 99.9% of the time, you're going to use a sequential multiplier that takes place over multiple cycles. And that's what's in the homework. And this is more of like a dummy example if you, for some reason, are dealing with like FinFETs, but you're also like too lazy to actually make like a good design. So it's like it's like you're given like, I don't know, a machete to cut like butter like from, I don't know, palm oil. Yeah. Anyways, okay, that was bad. Okay, do we have ideas? Feeling good?
Which index has the least significant bit?
0.
Okay, that's what I thought.
Yeah.
So then,
Yeah.
I guess like you can multiply like the least significant bit of like BI with like AI,
Mhm.
and then in the next second to last least significant bit, shift it to the left by 1, and then repeat, and then like have like some kind of like running like sum if that's possible,
Mhm.
keeping track of like the result, like your intermediate result.
Sure.
this
I don't know, like
low
how
bar.
feasible like a running sum would be.
Yeah.
So, there's probably ways to make it more efficient.
Okay, let's do it. Is it okay? Should we take a breather? Are we okay? I can't. I see a bunch of people on laptops. I don't know if it's because you're taking awesome notes or if it's because you're lost or what's going on. So can I get like a thumbs up? Okay, cool. Things are going okay. So great. For loop. What I'm thinking is probably just have maybe like if statement. So a mux. And we can just say like if b of I is 1. So if like the current index that we're looking at is 1, then we should probably like add it to y of 0. Something like this.
Oh, yeah, shit.
Except, yeah, we probably now need to shift this a of I value by like whatever our current index is. So now we can go and shift this by I. Is that what we're thinking? So let's go and test this. We might get...
I'm getting an invalid array access error.
Oh. So this is... Oh, that's this one. Okay. Should just work. Yeah. There we go. And I wonder if I hit optimize, that will... Well, wait, okay, actually instead of 8, let's do something a little more manageable. Also make this a parameter.
Dude, what?
We'll do 3. Minus 1. 2 times width minus 1. And width.
These error messages are so
Okay,
not helpful.
this is better. Okay, let's double check that this works. So now I don't know, I can pass in the value 2, now I can pass in the value 3, and we should see 6 at the end. Oh, it says unknown. Maybe I just need to enter. Okay. There we go, we got 6. Although, yeah, notice, right? We have a mux, and then we got an adder, and then another mux, and an adder, and a mux. Like, this is a very long operation. Like, this is going to take a very long time, adding all of this data together. So this is not the ideal way to really even make the combinational multiplier, but it's at least probably good enough for this. Okay, any questions on this? I think this is probably where I'll leave off today, and then we'll pick up on more like sequential stuff and more state machine stuff on Monday, unless anyone has some questions on this.
What would a better implementation look like?
You know, good question. I may link a really good textbook that talks about like 101 ways to perform like every possible arithmetic operation you can think of. I can do that, yeah. And now I don't remember what it's called. You can do like cool multi-operand adder algorithms that are really fast. I think that would probably be the best way. questions? Okay, actually, let's have a quick little discussion. So, right, so notice, right, we're adding a bunch of things in this for loop. But since it's a for loop, this is all combinational logic. So this will all take place over one single clock cycle. And note, since it's a really long chain of combinational logic, it's probably going to take a lot of time. So your clock is going to run really slow. A way to fix this would to have this take place over multiple cycles so that now it won't necessarily run any faster, but now it means that your clock speed will be higher.
Like in a CPU.
Sure, yeah. So, right, like this, you may be running at maybe 50 megahertz. Like this may take forever. So ideally, you should actually perform maybe just one single shift add operation per cycle. So maybe you could imagine there's some way that you could just insert some sort of thing that's all right, actually take a pause right here. Don't continue, wait until the next clock cycle. And what you'll probably want to do is not have a for loop, but instead probably have a counter where you just check what state you're currently in. It's are we in state 0? If so, then go and grab the 0th element and don't shift. If we are in state 6, then go and grab the 6th element and shift by 6 places. So that's how we can build a multiplier that takes place over multiple cycles, is we can swap out this combinational for loop with instead we can change it out for a counter with flip-flops. Yeah, leave it.
I guess I'm still kind of confused, intuitively, what your multiplication algorithm is doing right there. Can you explain that again?
Absolutely, yeah. So the idea is we are looking at the position of B, and we're, I think it'd be easier if I dot can it. All right. So what we are doing is we are grabbing a specific position of B. We're saying if it is a 0 in this place, then do not go and add this, do not add A. But if we find a 1 in this place, then do add A. And if the B is not in position 0, if it's in a later position, then what we need to do, instead of just adding A directly, is we need to shift it over. And that's actually exactly how regular multiplication works, is we just multiply that A value by that B index, but then shift it by a bunch of zeros. If we think even in base 10, if we have the value 1, 2, 3, 4, multiply it by the value 28. First you just multiply 8 by 1, 2, 3, 4. Then you multiply the value 20 by 1, 2, 3, 4. And then add those together.
Gotcha. Okay, yeah, that makes sense.
Sure. Okay. Any final things? Anyone angry at me? Or okay? Okay. Cool. In that case, class is over. If you have any questions, feel free to come up.